Welcome to Class 9. In this class, we'll talk about ACES, which is an emerging, high-end, generally movie production pipeline that basically replaces the Cineon DPX scheme that was used for years and years and years, for almost 20 years, for making movies. The origin of digital video effects, visual effects for movies, 20 years ago, the digital revolution took place just in the digital intermediate pipeline. Acquisition was on film and exhibition was on film. And over the last 20 years, we've had digital cameras introduced and digital projectors introduced. So slowly over that time, we've sort of adapted the whole pipeline to native digital. But in the era when film was scanned into digital form for manipulation and then recorded back out to film, it was common in the whole pipeline of the digital intermediate to perform the arithmetic on pixel values referenced to color science related to film photography. And when you do photography with the photochemical scheme on film and then scan it, you incorporate into the image data values the characteristics of the photochemical film. And those characteristics include crosstalk among the channels, what happens in the toe at very low exposure values, what happens in the shoulder at very high exposure values. In the old days of digital movie making, those characteristics got baked, as we would say in modern technology, into the image data values that are then dealt with in the whole pipeline. And as camera technology evolved to the point where we had feasible digital cinema acquisition directly without film, and as the projector technology progressed to the point where we had digital projection rivaling the characteristics of projected print film, it really started to become a bottleneck that the whole post-production process was built on this notion that the image data values had already had film characteristics buried in them. And so even 12 or 13 years ago, the really advanced companies in the industry started figuring this out. And they started figuring out that sort of filmish pipeline, and let me now backfill the correct word for that. Kodak introduced a system called Cineon involving film scanning and film recording. And the data values that became common for digital production of movies were in color terms called Cineon printing density, or CPD. Now, they were packaged up either in Cineon files, .cin, or probably more commonly in DPX files, where DPX should really be considered just a container for the image information. DPX really had nothing to do with the interpretation of the color values stored in that file. So we come to the ILM pipeline invented 12 or 13 years ago, where ILM realized that the correct way to do compositing and CGI and other image synthesis and image manipulation operations was in linear light space. And in previous classes, you've heard various things about linear light or scene referred or radiometric image encoding, really defined by an 18% card in the scene being assigned a data value 0.18 of the way between optical black and a perfect diffuse reflector. So that's what I'm calling linear light. So ILM figured out that that's the correct way to do the really CGI and VFX intensive parts of the pipeline. And they figured out that computer graphics were directly produced in that form, because in computer graphics, say ray tracing, for example, the correct way to do the arithmetic is to mimic the way that photons would interact with objects and lights and the camera in the scene. And all of that arithmetic is intrinsically linear light or radiometric. So 3D computer graphics comes directly into this domain. But if you capture film, you scan the film, then you need to basically unwrap the characteristics of the film to go into the scene referred domain. And roughly similarly, if you capture video, record in the old days, so keep in mind this block diagram is from 12 or 13 years ago, you would have undone the characteristic that the camera imposed to recover the radiometric scene linear values for use in VFX and CGI. Now, on the output side, there's a necessity for some processing and some color transforms. One of the necessary color transforms is just to go out to the scanned film, and that depends upon the characteristics of your film recorder. And another aspect, which is not really highlighted in this block diagram or even in this white paper, but another aspect is you need to do picture rendering. And so Florian Kainz and his colleagues at ILM published this diagram in a white paper called OpenEXR Color Management. And this really forms the conceptual foundation of the ACES pipeline you've already heard about. But some kind of polishing up was done, and the way that ACES does color transforms is slightly different. But this forms the genesis of the ACES idea. So now let's go and explore ACES in some detail. Now, Florian Kainz and ILM's OpenEXR Color Management paper was a seminal piece of work, really important and really good work. But looking back on it from today or even from 4 years ago, the color imaging community had developed a better understanding of the basic picture rendering operation. And you've already heard from the camera class about how if you're shooting in a really, really bright situation, but displaying in a dark situation, adjustments are necessary to overcome visual changes. So these are adjustments that I'm calling picture rendering, and this has kind of been an emerging area for the last 10 years or so. But the term picture rendering is now pretty well established. So the notion is that we're likely to come into this situation from, to have image data originated maybe with white at 30 nits. That would be typical of almost as dark as candlelit. 300 nit, which would be a reasonably bright situation, say in a studio, 3,000 nits, which would be an overcast day, and maybe as high as 30,000 nits, which would be a bright, clear, sunlit day in the middle of the day. So there's a huge range of luminance levels, and you've already heard that we set camera sensitivity and exposure to normalize white so that our range of data coming in has got diffuse white or white card white, paper white, almost up to the 1.0 level. We want a little bit of room for things that sparkle. But the image data has been normalized, let's say between the range 0 to 1. Now, an engineer or a mathematician or a physicist might think, well, you just need to display that information. So just drive that range 0 to 1 into an appropriate display. So if you had come in with a certain power function, you just go out through that power function. And for HD, the standard gamma would be 2.4. So just come in with 1 over 2.4, which is about 0.42. Well, that's not what we do. Because when you go out, you might be displaying consumer electronics with a white at maybe 300 nits. This would be a typical television set. HD studio display has got a white luminance of about 100 nits, and cinema has got a white luminance of maybe 30 nits. And there's a huge viewing shift from luminances like this to luminances like this. And basically what happens is colorfulness is lost at these lower luminances, and contrast is lost. And the way we overcome this typically is that we introduce overall end-to-end a power function. So if you think back to the grading class, mapping the range 0 to 1 to the range 0 to 1, what we do for the compensation of these visual effects is introduce a very slight gamma, and this will be familiar from kind of the master gamma knob on a grading system. And for a situation going from about 3,000 nits in a studio to about 100 nits mastering HD, the appropriate power function is about 1.2. And that's what I call the end-to-end power function. And that power function increases the colorfulness and increases the contrast to make it look like this is outdoors, even though it's only 100 nits. Now that overall 1.2 function is achieved in HD by going out to 2.4 gamma, and this is what you would get by default on an HD studio reference display. Now, those displays are adjustable to have anything from, say, 2.0 to probably 2.8, but 2.4 is the number standardized in BT1886. So that's the one you should use going out to 100 nits. That's the HD number. Now, theoretically, you would think, okay, that means the camera needs to be set to about a 0.42 function, but we don't do that. Instead, what we do is set the camera to about a 0.5 function, and then the relationship from the optoelectronic curve in the camera to the electro-optical curve, and some people call it transfer function or conversion function. The relationship between those two is just the product of those two numbers, 1.2. That 1.2 power function is the default baseline picture rendering for HD. Now, it's a confusing topic because that 1.2 number never shows up in the video standards. This 2.4 number shows up in BT1886, and this 0.5 number is the effective gamma function of BT709. However, BT709 includes a scaling and an offsetting and an insertion of a linear term, and the number that's actually in the equation is 0.45. But the real number that's effectively going on is 0.5. So, this issue of 1.2 power function for picture rendering in HD, it's not well understood among the HD experts. Now, the reason I'm going through this picture rendering scenario is really it's to give you the preamble to ACES, which is the emerging standard for digital cinema, post-production or DI, and to some extent it influences acquisition. And the central part of the ACES block diagram is exactly this picture rendering going from values representative of a light environment like the studio to values representative of a dim environment like cinema display. And so in the ACES Academy color encoding system, which is this whole pipeline, there's a central component which is called the rendering transform. And it's the goal that there will be exactly one of those rendering transforms. So it's version 1.0. Not to be confused with 1.2 power function. In fact, there's supposed to be only ever one of those rendering transforms, so we're calling it the reference rendering transform, the RRT. So this is in the ACES block diagram where the picture rendering takes place. Now, there's a bunch of other transforms. Here at this connection point on the way in is linear light, or you could call it, if you want to be fancy, radiometric, using the Academy color encoding specification primaries. And We talked about these the other day, and I showed you where those primaries lie on the CIEXY spectral diagram. The two of those primaries are non-physical, so it's an extremely wide gamut space. It covers all of the colors. And we don't have to say all of the visible colors because colors are by definition visible. Now, ACES refers to this particular color encoding specification, or loosely color space, but ACES has also been adopted as the acronym for the whole pipeline from one end to the other. So really ACES is kind of an ambiguous term. Now, linear light comes out of the rendering transform, but this is the OCES, the output color encoding specification. It's also wide gamut, high dynamic range, and it needs to be adapted to different display devices. So let's take, for example, a DCI P3 digital cinema projector. That projector has got its own electro-optical conversion function, which is 2.6 gamma, as we've discussed before. So in the ACES block diagram, what we need to come out into that is a color transform, which is a version of an output device transform, but this one going to a DCI P3 projector is, we call it the reference display transform. And this is the pipeline for cinema. Now, on the way into the RRT, of course, we've got cameras, and we can have cameras of various sorts, and some of them can be on tripods, and some of them can be on jibs, and some of them can be little tiny GoPro cameras. But we want to be in a situation where we come from different cameras, each with their own color coding, and these will typically be log curves. So we might have one camera having Sony log, another camera doing ARRI log C, and another camera doing GoPro or whatever their coding is. At the input to the ACES process, we have color transforms, which are taking different various camera spaces and mapping them into the ACES color space. And these are input device transforms. And they come in different flavors, and typically you'll try to obtain one of those transforms from your camera vendor. Now, there's also a sort of theoretical, and I'll put it in dotted lines, reference input capture device. So everybody, and that delivers ACES space directly from the scene. So everybody tries to mimic the reference input capture device with their various IDTs. And then you may have a Canon IDT, or who knows, there's going to be large numbers of IDTs for different cameras. So all of that information then gets normalized, and the idea is we're able to intercut among the cameras, making them look more or less the same. We then do the reference rendering transform to drop us from, say, let's say for the sake of argument, 3000 nit white down to, well, the peak in the cinema would be 48 nits, but white shirt white is more commonly portrayed at something like 24 nits, leaving room for the highlights. So that huge shift in light level from 3000 nits to 24 nits, that is compensated visually by the reference rendering transform. And then the output device transform goes out to that particular projector. Now, I'm sure you can see where we're headed here. There's going to be different ODTs. So one thing you can imagine, you could have an ODT directed to a 709 display, and it's got a little bit less color gamut because it's 709 space instead of P3 space. Both of these will be RGB, but they're different flavors of RGB. And 709 is associated with a 2.4 gamma, so its ODT will have to compensate for that. And you might imagine in the future, and I'll put these at kind of higher quality levels, you might imagine in the future going through an output device transform to a Dolby display for high dynamic range. And you might also imagine an ODT going out to a laser projector. Laser projector technology has been demonstrated for cinema, not yet commercially available, but it looks like it'll be pretty soon. So basically, there's a variety of IDTs depending on your camera, a variety of ODTs depending on your display device, but we've got this central rendering transform, which we hope we can lock down and only ever have one of these. Now, what's missing from this diagram is art or look or style. So the final piece of the ACES block diagram drops into this place in the diagram. So let's come out of here, go through the look modification transform, and then go back in to the RRT. And in some sense, this is optional because you can just run through the ACES baseline without imposing any style or look. But more commonly, you'll want to have a UI that's dialing in modifications for aesthetic purposes. So this can be style, it can be craft, it can be matching shot to shot to shot. Although if you do a spectacularly good job on the capture and the input, you might even find that these shots just match. But more commonly, you might want to do a white balance or an exposure compensation. And so this is all involved in the look manipulation transform. And I'm drawing 3 knobs here, or even 6 knobs, 3 trackballs and 3 master knobs, as if this is the grading, the basic grading console. And so you can imagine doing color grading, much as I've described in the earlier class, using this scheme. So the look management or look manipulation transform is really kind of an optional path through. Its input is in ACES space. Its output is in ACES space. And how a particular grading system vendor decides to implement the knobs and which knobs they provide and what color space those knobs are working in, that is not likely to be standardized. And so we'll likely have different working spaces that involve the color pixel values that those knobs affect, and that will be up to particular grading vendors. So there you have an overview of the ACES block diagram, and that's prefaced by our discussion a few moments ago about the basic picture rendering operation, including what I call the baseline rendering of HD, which is just accomplished by manipulating the gamma at the input and the output. So for many of you learning about this today, your goal will really be to produce an image at the approval stage at the end of grading where you are looking at a monitor that's based on science. So call this your studio reference display. I like using the acronym or the abbreviation SRD. And that's supposed to be science. And you hope that downstream is science, but you do recognize that some people will take your material and display them with different displays and different viewing conditions, and then different gamma values may very well be appropriate. And you've heard this story before, but let me leave you by ending today's class with this idea that at 100 nits we standardize 2.4 gamma. That's BT1886. If you're in a very, and I guess I should mention that HD mastering is assuming that the area surrounding the image that's affecting the visual system, but it's not part of the image, is very dark. And I like to think of HD viewing at the mastering stage as having a surround of about 1% of that 100 nits. So the surround is about 1 nit. And that surround you can think of as putting up the image, and that occupies maybe 30 degrees of your visual field. But your visual system is affected by what goes on around that. So think of putting the image up as the central tile of a 3x3. So think of the surround as being 1 picture height above, 1 picture width to the left and right, and maybe, I don't know what's down below the screen, but you could think of 1 picture width, 1 picture height below the screen. So this is the surround condition. And in HD, it's dark, but it's not black. Out in consumer space, the luminance of white is likely to be 300 nits, and there the sRGB standard standardizes gamma 2.2, and that's entirely appropriate for 300 nits at something like 5% surround. So instead of 1 nit surrounding the image, we've got 5% of 300, or about 15 nits. So quite a bit brighter. And then at cinema, I've already explained that let's call it the artistic white, might be 30 nits, even though the peak white would be 48, which is in the DCI standards. But cinema has got a 0% surround. And under those conditions, a gamma of 2.6 is appropriate. And that's exactly what is standardized in the DCI P3 spec, or otherwise known as SMPTE 431. So it's an important aspect of color science for imaging that you've got gamma values, 2.4 for HD standard, 2.2 for desktop computing, which is also effectively used in consumer electronic television, and 2.6 for digital cinema. And in some sense, you can think of mastering once for HD under those conditions of HD mastering, but then using that material in consumer electronics at 300 nits, and even potentially in a cinema at only 24 nits, and just changing the gamma to overcome different viewing condition and display luminance variations. So the gamma situation is complicated because at the back end, it deals with viewing conditions. And also in HD, effectively, if you're shooting at 30 nits, almost candlelight, 300 nits an interior, 3,000 nits a dark overcast day, and 30,000 nits at the beach, at Manly Beach in Sydney, say, you can overcome those variations with gamma if you're willing to adjust the gamma knob at the camera and lock down your image data, or you overcome those differences in the look modification transform for the ACES pipeline, or you overcome them in grading. So gamma has not only got a direct effect on visual contrast, it's also got an effect on colorfulness. The more you increase that gamma number, the more colorfulness you dial into the image. So that's the entire overview on ACES, and that's it for today's class.